Page 496, number 4. Each pair of functions f of x and g of x determine the h function as a combined function of f times g of x. So be careful of this. This means f times g. Please don't mistake this for the notation when it looks like this. That means f of g of x. Okay, so that's a composite function. This means multiplication. So we have multiplying these two functions together, and we want to sketch the graph of f, g, and h on the same set of coordinate axes. State the domain and range of the combined function of h. So we'll start with the domain and range of a. So when we take a look at f and g, they're both, one is a quadratic and one is a linear function. They both have a domain of all real numbers, and the range is going to be dependent on the vertex of the parabola. But when we combine these together, I end up with a cubic function. So the domain and range, the range of this cubic function for all cubics is going to be all real numbers. So my domain, I'm going to start with my domain. The domain is all real numbers, and the range is going to be all real numbers. And if I were to graph this, okay, so the parabola is f, the linear function is g. When I graph this, I'm going to get a cubic function, and the important parts of the cubic function are going to be the zeros. So I'm going to start with a zero. So in this case here, if I factor x plus 5, x squared plus 5x plus 6, it factors into x plus 3, x plus 2, and then I end up with an x plus 2. Okay, so this is part A. So this is my new equation. So I'm going to end up with zeros at -2 and -3. So -3, 0, -2, 0. Now, if I want to plug some other points in there, I can. But since this is a familiar function, I can just graph it using just the zeros. So I know I have a 0 here and here. Okay, and I know that this is a cubic function, so it's going to come up from the bottom. Since it's a positive leading coefficient, it's going to bounce, and then I'm going to have a y-intercept at 10. Maybe I should put the y-intercept in there. At 0, we have x equals not 10, but 12. Okay, so my graph is going to go through these points. It's going to come up through here. It's going to bounce, and then it's going to go up through there like that. Okay, so there's my cubic function for A. For B, I have the linear function and quadratic function. Again, for B, we're going to start with the domain and range. Since this is a cubic, it's going to end up being a cubic function. When I combine them together, my domain is going to be all real numbers. Okay, I started with all real numbers for both the quadratic and linear. The range, since it's a cubic function, is going to be all real numbers as well. The points that I want are going to be, since I know it's a cubic function, I could really just base it off the zeros. So writing it in factored form, I get x minus 3, x minus 3, x plus 3. So I'm going to just put my zeros at -3 and +3. And I also just put in my y-intercept just to make it easier to work with. My y-intercept is going to work out to be -20 or +27. It's going to go way off my graph. Okay, so maybe I'll scale this graph to, let's scale this to 50 and 25, -25 and -50 here. And my zeros are going to be at -3, +3. I'm going to have a bounce at -3. I know I have a leading coefficient of positive, so it's going to come up through -3. Okay, it's going to bounce at +3, so it's going to come up through here. It's going to go through 27, and it's going to come up through here like this. So again, if we want some more accuracy, we're going to plot a few more coordinates. Lastly, for C, I've got a composite function here. This is now, when I combine this together as multiplication, this is a rational function. It's going to have two factors that give us 0. So it's going to have vertical asymptotes at 0 from this one, and at -1 from the other factor here. So at -1, and again, maybe I'm going to scale this axis here. So let's make that -1 here, +1 to -2. So we're going to have our vertical asymptote at -1 through here like this. Okay, and then we can plot a few coordinates here. We know our horizontal asymptote for this type of rational function is going to be along 0. And it doesn't look like we have any zeros for this. So I'm going to plug a few random coordinates in here. So at x equals -2, when I plug that in, I'm going to end up with -1 in the denominator times -2 in the denominator. So I get +1/2. So at -2, +1/2, maybe right about here. Oops, +1/2 up here. So that tells me that this section of the graph is going to follow the asymptotes like this. Okay, I'm going to choose a point between -1 and 0, so maybe -0.5. So I'm going to end up with +0.5 in the denominator times -0.5 in the denominator. That's going to give me -0.25 in the denominator. I can put that in my calculator, but that's going to give me -4. Okay, so actually I'm going to scale this slightly differently again. Let's just make this the actual scale of 0.5 here, following the graph, and then at -0.5, we're going to be at -4. Okay, so we know that the graph is going to go through here something like this and follow the asymptotes. Again, we're not going to find the vertex because the vertex is going to be a little bit difficult to find. And then plugging in here, let's put in x is +2, or sorry, +1. And if when x is +1, we end up with 1/2 again. So down here, and we're going to follow the asymptotes again. Okay, so the better idea you have of the actual function that you're going to end up with, the less coordinates that you're going to need to be able to sketch a reasonable graph of this.